Good evening, Heart of England. This is Cosmic Rays. For the last half hour or so, we've been watching what's going on inside a cloud chamber, which is sitting here on the front bench, and we've been watching the arrival of cosmic rays, which is what this talk is all about. So let me kick off by switching to some PowerPoint. I'll be going backwards and forwards between PowerPoint and some demos on the front bench here. I'll be giving a little bit of an introduction. Before launching into what are cosmic rays and how do we detect them, etc., I think it's useful just to have a little bit of background as what we mean by radiation and radioactivity. So I'll be talking about terrestrial background radiation first to set the scene. Then I'll be talking about the history of cosmic rays, and then asking how do we actually detect them? What are these detectors that are on the front bench here? How do they work? And ultimately, if there are indeed these cosmic rays, these charged particles that appear to be raining down on the Earth, because we can see them here, where are they coming from? We can see them here at sea level, but where do they come from in the first place? We'll be asking about the cosmic sources of cosmic rays, and then I will summarize right at the end. So firstly, the HoEAS lawyers got in touch with me and said, you must have a risk assessment because I have some radioactive samples at the front here. They're protected inside a metal case at the moment. There is no risk to anybody in the audience. I will be using these radioactive samples shortly as part of the demonstration, and then I will put them to one side if you want to come closer and have a closer look at the cloud chamber after I've finished the talk. So I'm using a couple of detectors in this particular talk. On the left, what most people call a Geiger counter, and on the right, a cloud chamber, which I've built. And if anybody's interested in emulating this and wants to build a cloud chamber for themselves to see subatomic particles, well, the instructions are here as to how you can build yourself a cloud chamber for about 25, 30 quid, something like that. So let me start by switching the speaker back on for the Geiger counter. And hopefully, you will be able to hear occasional clicks, one every couple of seconds, perhaps. Background radiation. So this yellow box here at the front is what everybody tends to call a Geiger counter. Physicists tend to get rubbed up the wrong way when you call them Geiger counters because we should call them Geiger-Müller detectors. But let's not be too pedantic. Let's just stick to the idea that these things are Geiger counters. So what are you actually listening to with each click here? Given that the radioactive samples at the moment are well away from the Geiger counter, so you're not hearing radioactivity from the radioactive samples, you're hearing background radiation. Each click you can hear signals the arrival of a subatomic particle of some kind. Maybe that subatomic particle came from an atom that's lurking in this room, but that click you hear may well be, and probably is, a cosmic ray. And the source of these cosmic rays, well, it could be a supernova in our galaxy, or it could indeed be a black hole, possibly in another galaxy. Certainly, a long time ago, in a galaxy far, far away, a star might have died, or a black hole might have formed, and we are hearing the clicks as a result of that. The bottom line is a Geiger counter just clicks. It doesn't tell you what it is that it's just seen or heard or detected. All it tells you is something has passed through this detector. So the click itself doesn't tell you anything about the character of, for instance, which particle, which type of particle is it that's passed through the Geiger counter. That's why we have multiple types of detector. So let's cover a little bit for the first few minutes on background radiation. We have to remind ourselves that background radiation, by its very nature, is with us all the time. Background radiation is not necessarily something to be concerned about. We have to remind ourselves that the Earth is a radioactive planet. This is nothing to do with humans adding nuclear power stations or letting off nuclear bombs. The Earth was made radioactive, and it is still radioactive. It was radioactive 4.5 billion years ago, and it still is. It's a natural consequence of the way some elements in the periodic table behave. If we remind ourselves about the periodic table, 90-something stable elements, a lot of the elements in the periodic table are stable, by which we mean once you've made an atom, that atom is almost eternal. In other words, you can play around with the electrons in the atom, but the atom essentially stays that way forever. But there are some atoms, some elements in the periodic table that are unstable. They decay, which is a physicist's way of saying they change. We're not talking about them going moldy. We're talking about decay in the sense that one element can change into another element, and in the process spit out some subatomic particles. And that is effectively what we're hearing here. So let's have a look at a particular example. We're going to look at some uranium. And to start with, I'm going to show you a rather large piece of uranium. Let me go back to the camera. Oops. So now I'm looking at a piece of glass. It's a piece of uranium glass. In other words, it's a piece of glass that's been doped with uranium. Why should people put uranium in glass? Well, it's not because they want to make it radioactive. It's because it's a nice green color. Not only that, but it fluoresces like mad if you shine ultraviolet light on it. And for the benefit of anybody watching the video, not in the audience, I've just demonstrated that uranium glass fluoresces like crazy under ultraviolet light. It is definitely radioactive. We can tell that simply by putting it in front of the Geiger counter. It's not particularly active. In other words, it's perfectly safe to handle. It's got a few counts per second there, 10 counts per second. But this is a little bit large to put in the cloud chamber, so I'm not going to use that for the demonstration of actually seeing radioactivity. If I want to actually use the cloud chamber and see radioactivity, I need a smaller sample. So I'm going to choose a little piece of uranium ore. It's basically a rock dug out of the ground in Canada. And let me first just demonstrate that it is radioactive. Oops. By, again, putting it in front of the Geiger counter. So you can see perhaps that it's actually quite tiny. It's just a few millimeters in size. But it is quite definitely radioactive. And what I'm going to do now is place it into the cloud chamber and see what happens. Now, in order to do that, I've got to open the cloud chamber, which is going to unfortunately disturb it somewhat. And I'm hoping it doesn't disturb it enough to cause a problem. So now I simply have to waffle for a while whilst the cloud chamber sorts itself out. The cloud chamber is generating clouds of alcohol, and hopefully, as we saw with the cosmic rays, when particles are spat out by the radioactive elements in this particular uranium sample, we should see them leave tracks, because as it passes through the clouds, it'll produce little tracks. So let's actually see. We've got one. Okay, so it's only taken a minute or two. So we can already see lines that are emanating from this rock. The cosmic rays are still there. In the background, every once in a while, you'll still see a cosmic ray. But because this is a radioactive element, uranium inside this particular rock, you will see a lot more of them come from the rock than you will come from cosmic rays. So anything that basically appears to come from the rock is definitely radioactive. Anything that you happen to see in the background could well be a cosmic ray. After a little while, you may notice that although it is apparently spitting out a lot of subatomic particles here, or at least a lot of stuff, perhaps you notice after a little while that the stuff that it's spitting out appears to come in two different flavors. Sometimes it seems to be a very bright, very narrow track, and occasionally the track seems much more ghost-like and a little fatter, and perhaps not as distinct. So we might guess, even not knowing what this particular material is or understanding radioactivity, we might guess that whatever this is, it's spitting out two types of something. And I can switch back to PowerPoint, because although I had absolute confidence that the cloud chamber was going to work, just in case, I imaged a radioactive sample on my kitchen table, and in good Blue Peter fashion, here's one I prepared earlier. So again, we can see tracks coming out of this rock, some of which are very narrow, some of which are very broad. The fact that it's a much bigger rock is neither here nor there. It's about the same activity. But what I did with this video is take a minute or two of this video and then added up all of the frames of the video so you can see all the tracks at the same time. And now you can see that there are quite definitely narrow tracks coming out every once in a while, but also these much broader ghostly tracks. Again, indicating whatever's going on here, it's spitting out two types of something or another. And we can ask ourselves, well, what would we expect? Let me just get rid of the annoying clicks for the time being. So we can ask ourselves what's going on there. The rock is clearly emitting something, and they're leaving whatever's being spat out is leaving tracks in the detector. So we can ask ourselves what's actually going on here. Well, atoms, this is not a great picture, but it'll do. Atoms are essentially a positively charged nucleus surrounded by lots of negatively charged electrons buzzing around. And it's the nucleus alone that determines radioactivity. It's nothing whatsoever to do with the electrons buzzing around the nucleus. It doesn't matter how many there are. It doesn't matter if we take all those electrons away. The radioactivity of an element, whether it changes into another one, whether it spits out a subatomic particle, is all a function of that nucleus. And here's a rather busy looking graphic, and it's basically just to show that what can happen to a nucleus, which is a collection of protons and neutrons, the different colored balls here. An unstable nucleus, a nucleus that wants to be something else, wants to change into something else, can spit out all sorts of things. We're not going to see all of these, but just to give you an idea of what could, in principle, happen to a nucleus, it could spit out a proton. The number of protons in a nucleus determines which element it is we're talking about. Some nuclei don't like the number of protons they have, and so will spit one out in order to lower the energy and make it a little more stable. Alternatively, it might spit out a neutron, an uncharged particle. Again, if a nucleus has too many neutrons, it might spit one out. Also, alpha particles could be spat out. An alpha particle is simply two protons and two neutrons together. In other words, if a nucleus really wants to get rid of multiple protons and neutrons, it might well do that by shedding two at a time, two protons and two neutrons. That happens to be a very stable structure. It's also what we call the nucleus of a helium atom. So alpha particles are the same as the nucleus of a helium atom. A nucleus might also spit out electrons or their antimatter equivalent. Every particle, protons, neutrons, electrons, muons, whatever, all particles have an antimatter equivalent. In other words, they have all the same properties except they have the opposite electrical charge. So it might spit out an electron, the familiar electron that we all know and love, the electrons that are in our atoms, the electrons that flow in an electrical or electronic circuit. But it's also possible for a nucleus to spit out the antimatter equivalent of an electron. An electron in essentially all respects, except instead of having a negative charge, it has a positive charge. And it's also possible for a nucleus to spit out a gamma ray, a high-energy electromagnetic wave. Now, perhaps at school we can remember that when we learnt about radioactivity, we learnt about alpha, beta, and gamma radiation. So just to recap, alpha radiation, sometimes called alpha rays and sometimes called alpha particles, that's simply a historical note because when they were first discovered, it wasn't clear whether or not they were dealing with a wave, a bit like gamma rays, or whether they were dealing with physical particles like protons or electrons. So they were called originally alpha rays, and we still sometimes call them alpha rays or alpha particles. They are the nuclei of helium atoms, and they comprise two protons and two neutrons. They're quite heavy, and that means they interact very strongly with matter, which means they don't travel through matter very well. They can't even travel very far through air, let alone travel through a piece of paper or a piece of metal, for instance. Beta rays, again, or beta particles, it really doesn't matter, they're synonymous. Betas are electrons, either the electrons we're familiar with or their antimatter equivalent. They're rather lightweight particles, they can penetrate further than alphas, and as we've seen in the cloud chamber, they tend to rattle off like a pinball machine off the molecules in air. Gamma radiation is different from the previous two in that it is purely electromagnetic radiation. It's basically light of a very high energy or a very high frequency. So gamma rays are rather different. They are not charged particles, and cloud chambers are designed to see charged particles. So we don't see gamma rays in a cloud chamber. We might hear them click on the Geiger counter, but we don't see them in a cloud chamber. So if I just remind you, having established what we're looking at there, if we go back to the sample here, we are now a little bit clued up on what it is we're seeing. Whenever we see a very distinct line, relatively straight, sometimes a little bit curved, we're seeing betas. In other words, we're seeing electrons or their cousins. And whenever we're seeing a rather broader, rather more ghostly track, that indicates that we're seeing an alpha. Remember, even if gammas are coming out of this sample, we're not going to see them in a cloud chamber. So we can now get a good idea of what's going on with terrestrial radiation. And because I want to come back to cosmic rays later, I am now going to put that sample back in its box. And also make sure the box is well away from you so that if you want to approach the table later, you can. Okay. So let's just go back and remind ourselves where we'd got to. We said that when we're looking at a rock like this, terrestrial radiation, whenever we see tracks like that, we know they're betas. And whenever we see tracks like that, we know they're alphas. That would be true if we saw them in cosmics as well. If we see a very narrow track, it's probably an electron or something else. We are not going to see alphas in cosmic radiation simply because even if they are generated, they don't travel far through matter. They don't travel far through air, and they certainly cannot get through the glass of a cloud chamber. So even if they're generated out here, we'll not see them inside the cloud chamber. We're only seeing them here because I put a radioactive rock emitting alphas inside. Okay, let's have a little think about radioactive isotopes. Isotopes is the name we give to cousins of the same type of atom. For instance, if we take an example, let's think of carbon. You are made of shed loads of carbon. Carbon is an atom in which the nucleus of every atom has 6 protons, because that's a matter of definition. Any atom which has 6 protons in the nucleus is what we call carbon. If it has 6 neutrons as well, 6 plus 6 equals 12, we call that carbon-12. So you are made of a rather large amount of carbon-12. There's also a little bit of a different type of carbon. A cousin of carbon has a different number of neutrons. If a carbon nucleus has 8 neutrons, 6 plus 8 is 14, we call that carbon-14. That's the carbon we use in radiocarbon dating. If we want to know how old a tree is, for instance, that's been felled, we look at the amount of carbon-14, which is radioactive and changes over a period of thousands of years into something else because it's unstable and radioactive. We look at how much carbon-14 there is in this organic object compared to the amount of carbon-12, and knowing that it has a half-life of 5,700 years or so, we can work out when the tree died. So that's how radiocarbon dating works, because different atoms, different cousins, different isotopes of the same atom can allow us to look at stable atoms and radioactive atoms. If we look at the number of radioactive atoms that are around, some of them might surprise you. The radioactive atoms I'm going to be describing here, one of them is potassium. Maybe you didn't think of that as a radioactive material. It's one of the most abundant of the radioactive elements. In your body, at the moment, you probably are experiencing 4,000 atoms of potassium are decaying, are changing into something else. They're actually changing into argon. That doesn't particularly matter. And if you're worried that 4,000 per second sounds a lot, that is tiny compared to the number of atoms in your body, which is million. I don't know how many zeros are in there, but it is a tiny, tiny fraction. So you are quite safe, even though 4,000 atoms of potassium in your body are changing every second. It's one of the largest contributions to natural radiation. 2 other elements that I'm going to mention. Thorium is more abundant than uranium, and uranium is probably more abundant than you think. You might assume that uranium, which is at the tail end of the periodic table and obviously is used in either reactors or bombs or whatever, surely that must be very rare, otherwise there would be far more of it around. Well, actually, it's much more abundant than you think. 3 parts per million, that means there's 500 times more uranium in the world than there is gold. But it's economically viable to dig gold out of the ground, and it's much more expensive to dig uranium out of the ground, which is why you don't have quite as much of it around. But in terms of how much is in the Earth's crust, huge amounts of it. In the Earth's core, all of these elements, potassium, thorium, and uranium, are emitting radioactive particles. Because they are radioactive, they're emitting various particles, which is contributing to the heat of the core. That is what is keeping the core of the Earth molten. The core of the Earth is not molten because of any heat we're getting from the sun. That's irrelevant. It's molten because for billions of years, radioactive decay in the core has been keeping the core molten. And if you have a spinning molten core, then you have a dynamo. And if you have a dynamo, you have a magnetic field. So it's an interesting circle of life that radioactivity in the core provides us with a magnetic field, which to some extent protects us from radiation from the sun, which is an interesting little cycle there. Just a quick aside on what I'm talking about with antimatter. A very small fraction of potassium is a particular isotope called potassium-40. In other words, it has 40 protons and neutrons in the nucleus. And it emits beta plus radiation. Beta, similar to an electron, but plus indicates it's not a negatively charged electron, it's a positively charged anti-electron. It's an antimatter equivalent of an electron. So basically, any food rich in potassium, Brazil nuts, bananas, for instance, emit antimatter. If you've never thought of that, think of that next time you eat a banana. A banana is emitting antimatter radiation. And this gave rise to the banana equivalent dose. For those that are afraid of radiation, and when you're trying to work out very high levels of radiation, you might use particular units. But when you're talking about rather low levels of radiation, somebody said, well, rather than use the standard unit of sieverts or rads or rontgens or whatever, why don't we use the banana equivalent dose to give us an idea of how much radiation is received? So if eating a banana is the equivalent of one banana equivalent dose, you can ask the question, okay, we're being irradiated with cosmic rays. We've seen it over an area of a few square centimeters, but of course all of those particles are going through you as well. So you are being irradiated 24/7 with cosmic radiation. How much is that equivalent to eating one banana? And the answer is the cosmic ray dose that you get every day is equivalent to a couple of hands of bananas. So you can either double your amount of radiation by eating lots of bananas, or you can just say, okay, I'm getting the equivalent of a dozen or so bananas worth anyway. Actually, a little more than that if you fly a lot, because the radiation levels are somewhat higher at elevated altitudes. And the final point on terrestrial, before I move back to the main point of this talk, not all radioactive elements are necessarily solid, like the samples of uranium that I've got tucked away in that little box there. Radon is a gas that is formed from the decay of uranium, and uranium is found in a lot of rocks, not in very high abundance, not in very high concentrations, but wherever you find granite, you will probably find uranium, and uranium decays into radon. Radon is a gas, and so will bubble out of the rock into the atmosphere. So the radon concentration that you can expect, for instance, in this room, will depend on how much granite there is under your feet. If you go down to the southwest of England, where there's a lot of granite, you will probably find a large concentration of radon. Whereas here in the West Midlands and around where I live on Wirral, there's relatively little amount. The total number of radon atoms in this room might be 1 billion, which is tiny compared to the amount of oxygen and nitrogen, for instance. So yes, it will depend on how much granite's under your feet. Radon is a gas that's emitting alphas, and so the only way we could see an alpha in the cloud chamber is because radon is already in there. When I had it open, the cloud chamber had a whole load of air inside it. A tiny part of that air would have been radon, and that radon is producing alphas. So we might catch an alpha when we go back to that a little later. So that's the preparation. That's the background that reminds us about radioactive materials, radioactive rocks, and radioactivity. Now we can address the main point of this talk, which is, what are these cosmic rays all about? The pioneers of radioactivity, you could argue, are these three individuals. I would guess that you all recognize the person in the middle, Madame Curie. You might recognize the person on the left, Becquerel, who discovered radioactivity. I'm guessing you may not know the guy on the right, Victor Hess. So Becquerel discovered radioactivity in the late 1800s, and Marie Curie took up some of his work and basically extracted various radioactive elements, polonium, radium, radon, etc. Or at least radon was discovered around that time. But again, the contribution of Hess perhaps less well known. So towards the end of the 1800s, a number of people were measuring radiation. How do you measure radiation back in the 1800s? Well, one of the techniques they used was a so-called electroscope, a gold leaf electroscope. If you ignore the fact that it's inside a little bell jar which tries to stop any air currents getting to it, a gold leaf electroscope is basically just two gold leaves. And if you charge them up, like charges repel, so these two gold leaves will repel each other. And if you discharge it, then they'll collapse under gravity back and touch again. So by simply measuring the angle of those two gold leaves, you can tell whether they've been charged up or not. You can't necessarily tell whether they've been charged up positive or charged up negative, but you can tell they're charged if the two gold leaf strips separate. What was discovered in the late 1800s was whenever people charged up one of these by either getting a balloon or a cat or something and charging up the little gold leaf electroscope, they found they kept discharging. In other words, they left them on the bench and somehow extra charge, either extra positive or extra negative, was getting into the bell jar and discharging the gold leaf electroscope. So it was understood in the late 1800s there is such a thing as background radiation. But is this background radiation coming from above us, or is this background radiation coming from underneath our feet? That was not known at the time. So in 1910, Theodore Wolff said, okay, one way to tell is I'm going to take an electroscope, do a measurement at the bottom of the Eiffel Tower and see how quickly the leaves of the electroscope collapse, indicating how much radiation is around. And I'll do the same experiment at the top of the Eiffel Tower, which is quite a few hundred meters away from the ground. So that should tell us whether or not the radiation is coming from above or coming from below. When this experiment was done, it was rather inconclusive. In other words, it did seem to change, but by less than you would expect if the radiation was coming from beneath our feet. So a gold leaf electroscope is not accurate enough to see small changes to background radiation. And at the time it was questioned, well, is it going to be interfered with by the fact that, well, is the Eiffel Tower radioactive? That's not a silly question to ask. The Eiffel Tower is made of iron. Iron is dug out of the ground. Some of the ground is radioactive, so maybe the Eiffel Tower is radioactive. And haven't we just discovered this gas called radon, which is all around us? So is it possible that is it possible that the atmosphere is radioactive and affecting these measurements? So how do we tell whether it's above or below? This is where Hess steps in and says, if we want to determine whether or not this background radiation is above or below, the Eiffel Tower is not high enough. We need to go higher to see a bigger difference, to see what's actually going on. So that's his contribution. He designed detectors that would work even in a hot air balloon. So he did a similar experiment to Wolff. He basically said, let's measure the radiation levels at ground level, and then let's go up in a hot air balloon higher than the Eiffel Tower and see if the radiation levels go up or go down. So this is what he did in 1911 and 1912. In 1911, he went up to about 1,000 meters or so. And he again couldn't quite tell whether the radiation was going up or going down or leveling off. The changes were simply not enough to be definitively clear as to what was actually going on. So he said, okay, we need to go higher. So in 1912, he went up to 5,000 meters. Bam! The radiation levels increased significantly, and there was no question whatsoever that the radiation was coming from above. At 5,000 meters, there's no way any radiation from the ground or anything else down here could possibly affect the radiation levels being measured. So Hess determined that the radiation is coming from above. Right, it's coming from above, but where above? Is it coming from the sun, or is it coming from somewhere else? The sun was the most likely candidate. It emits a lot of light and heat. Maybe it emits a lot of charged particles as well. How are you going to tell? You've just done a balloon flight where you've shown that the radiation levels decrease when you go to altitude. If you want to know whether it's the sun or not, well, you do it at night. Who wants to go up in a hot air balloon at night where you can't see where you are, you can't see which way the wind is taking you, and you can't see where you're going to land? Correction, where you're going to crash because you can't see anything of what's going on. Nobody in their right mind would take a hot air balloon ride at night. So if you want to know if it's the sun or not, what's the solution? HoEAS came up with a brilliant idea. You take a hot air balloon flight on the day of an eclipse. Brilliant. You see whether or not, when the moon covers the sun, surely if you cover the sun, the radiation levels should drop if significant amounts of radiation are coming from the sun. That was done, and it effectively ruled out the sun as the radiation source. There might be a little bit of charged particle flux coming from the sun, but it's not responsible for most of what we see in background radiation. And for that, in 1936, HoEAS was awarded the Nobel Prize for essentially the discovery of cosmic radiation. He showed it came from above, and he ruled out the sun. Therefore, it's at the very least from somewhere else in the solar system or somewhere else in the galaxy or beyond. Genuinely cosmic. This is what we think is going on. This is an artist's impression. It's not a particularly good one for a couple of reasons, but it would indicate that somewhere up there at the top of our atmosphere, some charged particles are slamming into the atmosphere and producing a shower, a cascade, an avalanche, if you prefer, of secondary particles. Now, this particular picture is not good for a couple of reasons. One, it would sort of indicate that showers are going on all the time, including side by side, and it also indicates that the source is easily figured out simply by looking at where these are pointing, and it's always a bright star that's producing these. No, it's not quite that simple. So if you ignore the fact that the source isn't quite right, this is a reasonable indication of what we think is going on. Charged particles are out there in the cosmos, flying around. When they hit the Earth's atmosphere, they produce a shower. The picture on the right is a cartoon, a much simplified cartoon version of an air shower, an incoming so-called primary cosmic ray. This is the cosmic ray, the particle, whatever it may be, that's hitting the top of our atmosphere, tens of kilometers up. It strikes an atom of oxygen or nitrogen, and then it produces a whole shower of secondary particles. Every time one particle generates more, and they generate more, and they generate more, every time one particle generates more particles, the energy is shared amongst those particles. So if you were to work out the total energy of particles that reach the ground level and add them all up, you should find the energy of the incoming particle. This particular diagram is rather misleading simply because it only shows a few possibilities of particles being generated. It's unlikely that one incoming particle will generate half a dozen secondary particles. The previous image, the previous graphic, was a little more realistic. It might be that one incoming cosmic ray might produce thousands, more likely millions of secondary particles that ultimately will make it to sea level. Not only that, but a number of those particles will be unstable. Yes, it might be that some of the particles generated might be the familiar particles we know about. Protons, perhaps, which we know are the part of the nucleus of every atom. Electrons, which we know are part of atoms. But it transpires that most of these particles that are generated by a very energetic incoming particle, most of these new particles that are generated are very unstable and only live for a tiny fraction of a second. One of the most abundant particles that makes it to sea level is this muon. It's a cousin of the electron. It's related to the electron in that it has some of the similar properties, but it's much heavier. It's about 200 times heavier than an electron, which is why when we see it in a cloud chamber, it tends to be in a straight line, whereas electrons are much lighter, 200 times less mass, and they tend to bounce around inside the cloud chamber. Muons have no part to play in making atoms. Basically, if we see a muon in this room, we know it's the result of a cosmic ray. A muon only lives for a few millionths of a second, a couple of microseconds or so. So it might be made high up in the Earth's atmosphere. It then travels through the Earth's atmosphere, through the cloud chamber, through the table, through the floor, and eventually beds itself somewhere in the Earth's crust and dies. It decays some 1 or 2 microseconds later. So although it only lives a couple of microseconds, that's actually long enough for it to get from the top of the atmosphere down to sea level. And that's a picture I took a while ago, again, just in case the cloud chamber wasn't playing ball. That is a single frame of a video showing a muon, and we basically have a trail of droplets of alcohol as it passes through, much like an aircraft leaves a contrail in the sky. Here, a muon has left a contrail, a condensation trail of alcohol as it passes through the cloud chamber. So we've said that incoming primaries produce secondaries, and it's the secondaries that we see here and we hear on the Geiger counter and we see in the cloud chamber. But what are the primaries? What are the particles that are coming in that are producing these showers that we actually see here on the bench in front of us? Well, it's taken a few decades of research since cosmic rays were originally posited back in the early part of the last century. But we now know that most of these cosmic rays, most of these charged particles are protons. In other words, they are the nuclei of hydrogen atoms. Perhaps that's not surprising because we know hydrogen is the most abundant element in the universe. And 9% of the incoming cosmic rays are alpha particles, which are the nuclei of helium atoms. Again, perhaps no surprise, because helium is the second most abundant element in the universe. So if 90% are protons and 9% are alphas, all the remaining 1% are all of the other nuclei. In other words, they are nuclei of lithium, barium, boron, carbon, nitrogen, oxygen, etc. All the way throughout essentially the entire periodic table are represented. In other words, what's hitting the top of the atmosphere are effectively nuclei of all of the sort of atoms that we see, for instance, in the solar system. On Earth, we know that there are 92 naturally occurring elements, and essentially they're all represented in the cosmic ray flux. It's just that most of them are simply protons rather than anything more complex. So how do we go about detecting these cosmic rays? Well, one couple of detectors we've seen on the front bench there. One of them is the Geiger-Müller tube, otherwise known as the Geiger counter. What's going on inside this particular tube? Well, it's a tube full of some sort of an inert gas, a bit like maybe argon or something like that. And if we have an incoming particle of radiation or an incoming gamma ray, it can ionize whatever gas is in there and separate out the positive charge from the negative charge. So if we put a high voltage on a central electrode compared to the outer metal can, if we generate ions, positive and negative ions, by the ionization of the gas in there, the ionization, well, the negative charge goes one way, the positive charge goes the other way. We end up with a current flowing, and that yellow box basically just converts the current into a click. And it tells us something has happened, something has arrived. It gives us no other information. It doesn't tell us about the nature of the particle, it doesn't tell us the energy of the particle. It's just something arrived. And that's why they're called Geiger counters, because they're good for counting and knowing how many things have arrived, but not the nature of what it is you were dealing with. Cloud chambers are a little different. Where do cloud chambers come from? Well, the story goes that Charles Wilson, back in 1894, was standing on the top of Ben Nevis and looked out and saw the Brocken spectre. In other words, if the sun is behind you and it's a very misty day or misty conditions at the top of the mountain, when you look in the direction of your shadow, you might see a glory, a whole load of rings around your head, different colors. Not quite a rainbow, it's not quite the same structure as a rainbow, but it sometimes has the colors of a rainbow, but it has, because of diffraction, because of the nature of the way light is going past your head and into the cloud in the distance, you get not only a rather strange shadow, you also get this glow around the shadow of your head. So in 1894, he saw this Brocken spectre and he said, I'd like to know more about this. I'd like to understand exactly how this ring structure comes to be. Why does it look like that? Why is it different to a rainbow? Can I reproduce this? He didn't want to take all of his equipment up to the top of Ben Nevis. He said, is there an easier way of taking the clouds up there and putting the clouds into my laboratory so I can study Brocken spectres more clearly? So he said, right, I'm going to make a cloud chamber and I'm going to study clouds in the laboratory. So in 1911, he perfected a cloud chamber. But it wasn't long before he said, well, I'm trying to understand these Brocken specters, but every time I switch this damn thing on, I get these tracks coming through. I get these lines indicating that something is passing through my cloud chamber. And it wasn't long before he realized that this is the charged particles that are background radiation. And so for the first time, it was now possible that physicists could not only deduce the existence of subatomic particles that can't be seen, now you can see tracks and you can follow them and you can see how they interact with each other. And if you put a magnetic field on your cloud chamber, you can see whether the particles bend to the left or bend to the right, which tells you whether your charged particles are charged with a negative charge or charged with a positive charge. So it's now possible to do physics experiments and see what is going on rather than just hypothesize what you think is going on. And for that, Wilson was awarded in 1927 the Nobel Prize for, quote, the most original and wonderful instrument in scientific history. That's a hell of a citation for anybody. And his version of the cloud chamber back in 1911 has morphed somewhat into this version, a somewhat cheaper version that uses the technology of today. In other words, the technology available to Wilson. He tried to cool the gas by expanding, and the expansion cooled the gas. I'm using little semiconductor modules at the bottom here to cool the bottom of my cloud chamber to give me the same effect. So I'm not going to go into a huge amount of detail about how this is built because everything you need to know about how to build one is in the instructions here. But effectively, my little cloud chamber, yes, I know it looks like something that if NASA wanted to land a cafetiere on the moon, that's what they would do. But this particular cloud chamber is basically just a chamber in which I've put alcohol to make clouds. It's heated at the top, so the alcohol evaporates. It's cooled at the bottom to about -25, so the alcohol starts to condense. And somewhere in between, just above the cold plate there, the conditions are just right so that any charged particle that flies through the cloud chamber will leave a trail of alcohol droplets, and that's what we see with the tracks. So let's just temporarily switch back and see whether or not it's now playing ball again. We should have gone back now to, yep, okay, oops. Yep, so whenever we see a track, hopefully once every second or two, some of them are very clear, that one from top left to bottom right, etc. Every once in a while, we'll see other ones. Sometimes we'll only see a very short track, indicating that it's coming essentially vertically from above. If we see a long track, that indicates the cosmic ray is coming in more from the side. Notice that it doesn't really matter how much material it's coming through. It's already come through a fair bit of atmosphere. It has no problem coming through the roof. It has no problem coming through the walls. After it's passed through the cloud chamber, it will go into the Earth's crust and will travel quite some distance before it finally gives up its energy. So the cloud chamber, a wonderful instrument for allowing us to visualize what these cosmic rays are actually doing. So again, a video I prepared on my kitchen table. A few different things are visible, a nice muon there, and a lovely proton coming in on the right-hand side. And I let this video run when I was putting it and testing it and checking everything worked correctly a few months back. I ran this for quite a while, and then I took a fairly long video, and then I took each of the tracks that I could see and stacked them all together to give an idea of, over a long period of time, many, many minutes, what you might see in a cloud chamber. And that was the result. Hundreds of tracks. So yes, maybe one a second, maybe one every 2 seconds, maybe 2 a second. But you see some straight tracks, which are protons, lots of wiggly tracks. There's so many in this integration of all the tracks over half an hour or something that there's just too many to see, and you can hardly separate which ones are electrons and which ones are muons. It's only the bright ones that really stand out in this sort of image. But it's a reminder that if you were to watch this for half an hour, you would see an awful lot of action going on in these cloud chambers. So that's how it was originally designed, that's how it was originally put together by Wilson, and this is my particular version of it. But how do the professionals study cosmic rays? They don't have lots of these on their kitchen tables that they take photographs of. There are various ways you can determine what cosmic rays are up to. For instance, there's cosmic ray detectors on the Voyagers. I think they have just been switched off, but for the last 50 years or so, they've been sending back information. And because of the interaction of the way the sun generates a magnetic field, which affects the way cosmic rays come into our solar system, it was in 2012, Voyager 1 measured a significant change in the cosmic ray flux that it was measuring essentially day by day, indicating that it had passed outside the influence of the sun and was now in interstellar space. So it was seeing galactic cosmic rays, and a particular jump in the flux told it it had passed through the influence of the sun. If you prefer, had exited the solar system. Voyager 2 did the same thing, but Voyager 2 is traveling more slowly. Voyager 2, if you remember, went not only to Jupiter and Saturn, but also used a gravity assist from Saturn to go on to Uranus and Neptune. When it passed Neptune, it actually slowed down. It didn't use a gravity assist to speed up. It actually slowed down because it wanted to see Triton. And so Voyager 2 is actually traveling more slowly than Voyager 1, so it took a little longer to get to an equivalent point. So Voyager 2 measured a similar change in cosmic ray flux, indicating that it had left the solar system a few years later in 2018. There are cosmic ray detectors. For instance, there's one sitting there on the International Space Station. You can't really see what it is there. I can show you a slightly different picture. You can get an idea of its scale just by looking at the astronaut at the top there. The astronaut, I don't think, is doing anything to the particular cosmic ray experiment. It's just an interesting way of getting the scale. This particular spectrometer, this particular detector, is detecting particles that are arriving at the space station, which is essentially above the atmosphere. Well, technically it's in the atmosphere, but it's above most of the atmosphere. So anything you measure up there is giving you a pretty good indication of what particles are arriving and then producing these showers in the Earth's atmosphere. So that's how we know that most of cosmic rays are protons and some of them are alpha particles. What do we do at ground level? Well, there are a number of observatories for cosmic rays around the world. One of the largest is the Pierre Auger Observatory in Argentina. And again, an artist's impression gives you an indication of what's going on. If a cosmic ray comes in and slams into the Earth's atmosphere, it produces a shower of secondary particles, and there's lots of detectors spread over a large area of ground to try and pick up these secondary particles. My little cloud chamber here is just a few square centimeters in size, so we'll only pick up a tiny fraction of all the cosmic rays that are being generated by a cosmic ray shower. But this particular collection of detectors, that's what the individual detectors look like, they're spread over a huge area. And I'm sure you're not that familiar with Argentina to work out what area that is, but roughly speaking, it's the area of Luxembourg. So it's a huge footprint over which these detectors are sitting. These are not cloud chambers, these are large tubs of water. How do you detect the particle passing through a tub of water? Well, when particles travel through water, they can produce a flash of light by the same idea, the same analog, if you like, as what would happen if an object moves through the air faster than sound can move in air. What's the result? You get a sonic shock wave. And it's the same idea with light. If it's possible for a particle to travel through water, or indeed travel through air, faster than light can travel through water or travel through air. Remember, light slows down effectively when it's traveling through a medium, so nothing can travel faster than light in a vacuum. But when you're traveling through water, or whether you're traveling through air, it is possible for a particle to actually outpace light. And just like you get a sonic boom when you're dealing with sound in air, you can get the equivalent with light, a photonic boom. A photonic shock wave can result from a particle traveling through water or traveling through air faster than light can travel. And this particular type of light is called Cherenkov radiation. And here's a little idea. If we've got an incoming cosmic ray, what might happen is that the cosmic ray produces a shower. It splits into 2, which then generates 4, which then generates 8. And if these energetic particles travel faster than light, they produce a photonic boom, a flash of blue light. It's called Cherenkov radiation, or Cherenkov light, if you prefer. And this is a very much slowed down animation of what's actually going on. As a shower is generated, you get this flash of blue light in something like a billionth of a second or thereabouts. There are telescope arrays in the Atacama Desert and in the Canary Islands on La Palma to try and detect this flash of light in the sky. So it's not looking to see in which direction did they come, it's looking for, can we see a flash in the air because of a particle traveling through the air faster than light can travel through the air. And so there's lots of telescopes, a whole load on the Canary Islands, a whole load being built in the Atacama Desert. They're not complete yet, they're still being built up, but all of these telescopes are looking into the sky to see if they can see these characteristic blue flashes that tell you about the particles that are traveling through the Earth's atmosphere. And it works in the air, it works in water, as I showed you from the Pierre Auger Observatory. These tanks, these tubs are full of water and they're looking for the blue flash in the water. It doesn't really matter whether the water is liquid or solid, the blue flash will still occur. And one of the experiments being conducted at the moment is at the South Pole. It's called the Ice Cube Laboratory, sitting on top of the ice pack in Antarctica. The ice pack is something like 2 kilometers thick, so there's the bedrock underneath the ice pack. And for scale, there's the Empire State Building, just so you can get an idea of this, what's going on. They have instrumented by drilling into the ice and putting loads of photodetectors, they're looking like transparent footballs here, loads of photodetectors have been put into the ice to instrument a large cube of ice, roughly 1 kilometer across, 1 kilometer across, 1 kilometer deep. So it's a 1 kilometer cubed ice cube, which is why it's called the Ice Cube Laboratory. And anything that passes through that 1 cubic kilometer will produce a blue flash if the particles are energetic enough. And quite a lot of these particles will be energetic enough to produce a blue flash. So this animation shows what's going on. These lines represent all of the photodetectors in the cubic kilometer of ice. If a fast particle comes in, it generates a blue light shock wave, the Cherenkov radiation, and various photodetectors will pick up that blue flash. And because of the geometry and because of the timing of when these particular detectors saw the blue flash, you can reconstruct where that particular incoming particle came from. Did it come from the sun? Did it come from the center of the Milky Way? Did it come from somewhere else? So with this sort of geometry, you can start to reconstruct where are these particles coming from. Which brings us to the last section here. Okay, we can see these cosmic rays at ground level. We know these cosmic rays are hitting the top of the atmosphere. Where are they coming from in the first place? Hopefully, this combination of having experiments at ground level and experiments in space should be able to answer the question, where are they coming from? And for the most energetic of cosmic rays, how do they get that much energy? As a little aside, let's just remind ourselves that it was 100 years, give or take a month, 100 years ago that Hubble said we can now establish the distance to these spiral nebula that we see dotted around our skies. They are truly cosmic in the sense they are not inside the Milky Way. These spiral nebula are galaxies in their own right. This was first published in November 1924, just over 100 years ago. So this put the nail in the coffin of the great debate, which now established the fact that we live in the Milky Way galaxy and there are billions, if not trillions, of other galaxies out there. How is that relevant to our argument about cosmic rays? Well, we've established from Hess's work that they're not really coming from the sun, or at least only the low energy stuff is coming from the sun. So the question, are they coming from the Milky Way or somewhere else? The question is now that Hubble has told us that the universe is a lot bigger than we first thought, it's not just the Milky Way, there's an awful lot of stuff out there, we can ask the questions, are cosmic rays galactic? Are they coming from the Milky Way, or are they extragalactic? Are they coming from other galaxies well beyond the Milky Way? How are we going to tell? Well, we do as many experiments as possible, and we also need theorists to give us an idea of where they might be coming from. So theorists have said, if you want to accelerate charged particles so they have a lot of energy when they reach the Earth to produce a big shower and produce lots of these hits at ground level in the observatories that I've been describing, you need a fairly energetic, a fairly violent event to accelerate charged particles. Presumably supernova or the jets from supermassive black holes. We know they exist, we know they're quite energetic. Maybe they are the mechanisms by which charged particles get accelerated. The details are a little bit, I would say, iffy, but then I'm an experimental physicist. Theorists are trying to work out how it might be that shock waves from a supernova or shock waves from the jets of a supermassive black hole might conceivably accelerate charged particles up to very high speeds. But this is still, at the moment, conjecture. So when we ask ourselves about cosmic sources, you might say, well, surely that's easy. All we have to do is to run a few experiments, see a few showers, and then, by the method I mentioned just a few slides ago, we can figure out which direction they came from geometry effectively, and then we can say, right, if we have enough of them, we can figure out that the source of these cosmic rays is that supernova or that galaxy or something else we didn't know about. But the problem is, unfortunately, we're dealing with charged particles, particles that are charged positively or charged negatively, and they are deflected by magnetic fields. We know that from physics experiments in the laboratory. That's how cathode ray tubes work. Remember the old TVs before flat screen TVs? An electron beam was generated and then deflected by magnetic fields to give you a raster on your TV screen. Magnetic fields are everywhere. Yes, we have magnetic fields around the Earth, and that's responsible for protecting us from some of the low energy radiation from the sun. But unfortunately, magnetic fields are everywhere in the universe, to the best of our knowledge. And we are fairly ignorant as to what's going on. Now, in the laboratory, we can say, how do we measure a magnetic field, or how do we see a magnetic field? How do we visualize a magnetic field? Well, if we want to visualize the magnetic field around a bar magnet, we simply get iron filings. So if we had iron filings out in the galaxy, we'd be able to work out where the magnetic fields were. Not quite as silly as it sounds, because we've got something almost as good. We've got dust, and dust does tend to align itself in the local magnetic field. So the work of Planck and other satellites have given us an idea of what the magnetic field in the Milky Way looks like. But it is unfortunately very complex compared to the magnetic field of the Earth, and we don't have a good three-dimensional map of how the magnetic field looks, and that's what we would need if we want to work out how particular particles are being deflected by magnetic fields. We need to be able to map the magnetic fields. And that's the problem. And not only have we not got a good idea of what's going on within our galaxy, we've got no idea of what's going on in between galaxies. If these cosmic rays are indeed coming from another galaxy, then in order to work out how they've traveled from there to us, we would need to know what these magnetic fields are, so we can work out how a particle would be deflected before it finally arrives at Earth. We can't expect them to travel in straight lines, so we can't simply say this shower seems to point back to that particular object in the sky. But we need to understand the energy of the cosmic rays, because there is a ray of hope, if you excuse the pun, and that is it might be the most energetic particles. We know from our physics experiments in the laboratory, we know that the most energetic particles are deflected the least in any given magnetic field. So if we don't know what the magnetic fields are, let's simply go for the most energetic cosmic ray we can see, because hopefully that will have traveled in a straight line. And so we'll be able to point back to where it came from. Just to give you an idea of energies, visible light, such as the visible light that's hitting the screen here, has an energy which physicists use units of eV. We're not going to worry about why we use that unit. That is just the energy of visible light. X-rays are 1,000 times more energetic, and of course they can penetrate matter rather more than visible light can. 1,000,000 times more energetic than visible photons are the sort of particles that we've seen in alpha, beta, gamma, for instance, the sort of things that we've seen spat out of a uranium sample. They have 1,000,000 times as much energy as visible light. Where do cosmic rays fit onto this spectrum? Everything from there upwards. In other words, a billion, a trillion, a quadrillion, a pentillion, everything up to these ridiculous numbers of 10 to the power 21 times as energetic as a visible photon. And just to get an idea of scale, the Large Hadron Collider can accelerate particles up to about this energy. And if they build another one even bigger, the FCC, the Future Circular Collider, it might be energetic enough to reach the second arrow. But you can see the most energetic cosmic rays that we know about are much more energetic than anything we can create on Earth. But it's really these really high energy ones that we want to concentrate on if we want to be sure that they are traveling in straight lines across the universe. This is what we think the flux of cosmic rays looks like, and here I've color-coded these. The lowest energy ones probably are coming from the sun. The middle energies are probably coming from the galaxy, though we're not sure. And the highest energy cosmic rays are possibly coming from other galaxies, but again, we're not really sure. But the flux is such that the low energy stuff, well, there's loads of that arriving. We're seeing some of it in the cloud chamber here. At the low energy, we might get 1 particle per square meter per second hitting the top of the atmosphere. Loads of showers being generated. But at the medium energies, we're only getting 1 per square meter per year impacting the atmosphere, rather more tricky to see. And at the very high energies, we're only getting 1 per square kilometer per year, not per square meter per year. So these so-called ultra-high energies, these really energetic ones, which are the ones we really want to catch, we're not going to get many of those. But we have seen a few of them. Back in 2003, it was APOD explaining what they had seen in an earlier data run from 2021. The telescope array in Utah saw this shower. This is an artist's impression of the shower. What this array of detectors actually saw was a little bit of that shower, but by looking at the timing of when these things fired, they could work out which direction this was coming from. This is the Amaterasu, or Amaterasu, or that's a Japanese sun goddess, meaning shining from heaven. And the Amaterasu event should certainly not be confused with the tiramisu event, which is something altogether different. The Amaterasu event is one of the most energetic events ever documented in terms of how much energy must that original particle have had in order to produce the signal that we see in the array there. So they said, right, okay, now we have our chance. We've just seen this particular event, really high energy, right at the top end of what I was showing in that cosmic energy scale. And hopefully they should be deflected very little. And so we should be able to trace back, knowing the geometry of this particular event. And the question then is, right, now we've got it. What does it actually point at? And they found that it actually pointed at nothing. They could not identify any supernova. They could not identify any supermassive black hole in a galaxy that would explain the Amaterasu event. So does that mean, well, it means we need more data, basically. Does it mean that supernova and black holes are not the sources of cosmic rays? Or does it mean they are the sources, but they're being deflected by rather more than we appreciated? Maybe the magnetic fields out there are much stronger than we first thought, and they are bending, and hence what we think is coming from that direction, it actually came from over there, many degrees away, and hence we can't really pin down where they're coming from. So more work is necessary to look at showers like this to try and trace back, and as well, we need more and better theory as to what cosmic sources do we think might be producing events like this. The Amaterasu event was not the most energetic event ever seen. There was an event that was about 50% more energetic than that, seen a few years earlier. And if we ask ourselves, if we take the most energetic event, high energy means it must have been traveling close to the speed of light. That's how it works. The closer you get to the speed of light, the higher the energy of the particle involved. The most energetic event ever seen was called the oh my God particle, because when it was first seen, the scientists literally could not believe that any individual particle, a subatomic particle, could possibly have the amount of energy that they had recorded. So that's how it got that particular name. And to put it into some sort of perspective, let me finish in the next 5 minutes, just to give you an idea of how fast these particles are traveling. If it had the amount of energy that we're talking about, either for the oh my god particle or for the Amaterasu event, how close to the speed of light was it traveling? Well, they can calculate that. If you know the energy, let's assume it's a proton, then we can calculate how fast it must have been moving. As a percentage of the speed of light, it turned out to be 99.9999999. We're not done yet. 999. Still not done. 999. 999. We're nearly there, don't worry. 995% of the speed of light. That's the calculated speed of the oh my god particle. And the question is, what could possibly be the mechanism that will accelerate a proton up to that speed? We really don't know how that could possibly happen. Theorists can hypothesize, but we do not have enough evidence to tell us how that can actually happen. And I'll finish by attempting to visualize just how fast that is. We can count the number of nines, fine, but just to give you an idea of how fast that is, imagine we had the oh my god particle in a race with a photon of light. Let's have a racetrack through a perfect vacuum of 100,000 light years, roughly the size of the galaxy. And we are going to have a race between a photon of light, which travels at the speed of light, of course, and one of these cosmic rays. They are going to start this 100,000 light year race at exactly the same time. We're going to allow them to race for 100,000 years until the light crosses the finishing line. When the light crosses the finishing line, how far behind it is the cosmic ray? And the answer is, if you do that calculation, how much ground does it lose after traveling 100,000 light years? The answer is 5 millimeters. If you prefer it in terms of time, after a race lasting 100,000 years, the cosmic ray is behind it by less than a nanosecond. It's actually only a few picoseconds, a few trillionths of a second behind it after 100,000 years. That gives you a way of sort of trying to visualize just how fast these cosmic rays are traveling. And the question is, how do they gain that energy? And the answer is simple enough: we don't know. So in summary, cosmic rays are accelerated somewhere, somehow. We don't know what is doing the accelerating, and we don't know where these sources are, because at the moment we simply do not have enough data. It is thought by a number of people, surely supernova or supermassive black hole jets coming from supermassive black hole event horizons, surely they are the most energetic things that we know about. Quasars are the most energetic things we know about, and they are the result of jets from supermassive black holes. These jets are slamming into the intergalactic medium and are producing shock waves. Is it these shock waves that are accelerating the particles? The bottom line is we don't know. We know that cosmic rays can be deflected by magnetic fields. We would assume that low energy particles have their paths completely scrambled because they're deflected so much, and we assume the high energy particles would travel in much straighter lines. We know that the low energy particles in particular are sometimes deflected by Earth's magnetic field, which protects us to some extent, but some particles do definitely make it past Earth's protective magnetic field. We see the aurora from time to time, indicating that charged particles do make it into the Earth's atmosphere. And we know that when a charged particle hits the top of the Earth's atmosphere, it generates an air shower of secondary particles. Some of those secondary particles make it to sea level. A surprisingly large number of them make it to sea level, because muons only live for a couple of microseconds, and you might say, well, how do they travel tens of thousands of kilometers in only 2 microseconds? Doesn't that mean they're traveling really fast? Well, they're traveling close to the speed of light, but it's good old-fashioned time dilation that allows them to live long enough to actually arrive at sea level. So we have particles like muons and also some electrons and protons, the more familiar subatomic particles for us, and they make clicks in Geiger counters, and they make tracks in cloud chambers. So in other words, we can see them passing through the cloud chamber. We can hear them click as they go through a Geiger counter. So the cosmos apparently is full of charged particles that are flying everywhere. We know there's light everywhere because we're used to the idea that we can see the stars, we can build telescopes, we can see galaxies. We have space telescopes that work in the visible or the ultraviolet or the infrared part of the spectrum. But as well as lots of electromagnetic radiation flying around, there are also some charged particles flying around, some of them very energetic. We can see them in cloud chambers if we build one for a few pounds and then sit and watch them, or we can listen to a Geiger counter. Remember, each click signals the arrival of a subatomic particle that may well have started its journey in a supernova or in a supermassive black hole in another galaxy altogether. So when you're hearing the clicks, in a sense, you're listening to the universe. Thank you for listening.